Welcome everyone for the next session. In this session, we'll talk about spatial coherence. But let us try to differentiate what is the temporal coherence and spatial coherence. That's what we have learned till now. So let me just write one table. So in the left hand side, I write about temporal coherence, and on the right, I write about spatial coherence. Okay. So, what is temporal coherence? It is the ability of the wave to interfere with a delayed copy of the same wave. Okay. So, if you want to interfere or superpose, you mean with a specific interferogram, a pattern kind of thing with the same wave, but it is actually delayed with the function tau, right? So that is known as temporal coherence. So you get degree of correlation with that thing. Now, what do you mean by spatial coherence? So it is the ability of two parts, okay, of a wavefront. Now we talk about start talking about wavefronts, right? So I will just define what is a wavefront in some time. At different points in space to produce interference pattern. Okay. So if you actually see any of this, for example, there is a huge pond, and over there you actually drop a stone. So what do you see over there? So you will see such kind of waves that is propagating, right? And that these things are actually known as wavefronts. Okay, the peaks of that waves that you see that is propagating is known as a wavefront, right? So now what is asking is that you need to have 2 points, right? For example, this could be the point A and this could be the point B, okay? And over there I am going to perform a correlation, right? And it has to be in the same wavefront, right? So if there is any bend in that wavefront, then we can say that it is having a lower spatial coherence, okay? To define or to differentiate or to quantify this temporal coherence, what do we use? We use autocorrelation. Okay, that is you use the correlation with mutual coherence along with the same function. For the spatial coherence, we use cross correlation. Okay, so both are the function of the correlation, and you will see that mutual coherence function again come into the picture, but for different spatial positions and the same time in this case in the spatial coherence. Okay, so it is the overlapping of the same wave, but it is shifted in space instead of time. Okay. Okay, so let me write how do you quantify the spatial coherence. So you start with gamma of 1 to now. This is to differentiate the temporal coherence. Okay, so you just need to write it in the form of, again it will be using average, the conjugate of the electrical field at position R1 at time t, and then you have at some t plus delta t. Okay, now we actually normalize it. Okay, and what we find is that you have R12 nothing but R1 of R2 is given by gamma of R1, R2 and tau, and then divided by I into R1 into I into R2. Okay. So this is how you define your spatial coherence, right. One of the example of how do you measure this spatial coherence is given by Young's double slit experiment. So if you remember the Young's double slit experiment, so what happens in that is that you have two slits. So this is the obstruction, okay, and you are trying to pass plane wave. It could be, for example, a wave that is flowing in the water, and then there are two pathways that can go. So it, for example, what we are doing is that in our wavefront we are trying to examine 2 points which are spatially spaced out, right. So we do that, and once it passes through that empty space, it will give you something like this, okay. And once it interacts with any of these any of these plane which can actually act as a detector or a detector film, so you can see some kind of patterns falling, okay. This is the interference pattern again. Okay, so we try to see two different spatial locations of the same wavefront, and then we try to see how, when it is like, how far can we go with this spatially distance, how can it be spaced apart, so that still but you actually get your interference pattern, okay. So here we actually can say that we actually compare from two locations on the same wavefront, okay. So yeah. Now one of the example that you would see for finding the spatial coherence is nothing but the speckle. So speckle are the dot kind of a rough spots that you see once you shine the laser on any of the wall. So if you are very far away, then and you shine it the laser on the wall, you will see that there are a lot of red spots on the wall. So it's no more a kind of a Gaussian distribution, but it's kind of a lot of red dots that you see on the wall, right. So what does happen in that case? So in that speckle generation, what happens is that the wall is kind of having a rough surface, right, and what you shine on the wall is the light source with the flat wavefront, okay. But when it interacts with the rough surface, there would be scattering in different directions because of the surface being rough, right. So you have the wavefronts from various directions overlapping with each other, okay. And what you actually get because of this overlap is something known as an interference pattern, and that actually leads to that spotty grainy image that you see on the wall, and that is nothing but the interference or the speckle. Now that is the case when we talk about on the wall, the rough surface on the wall. But what happens when you shine the laser on the skin, on the surface of the skin, right. So on the surface of the skin, below the surface of the skin, we have many organelles, okay, and over there you again shine the light which is having a flat wavefront, but once it interacts with these particles, now these particles are also non-uniform, it is heterogeneous, and the dimension of the particle also changes. Now this all leads to the interference, it results into scattering, and the direction of the wavefront after the interaction will also be different, okay. For example, one would be in this direction, another would be in this direction, okay. And again what you will see is the interference pattern again, okay. So this interference pattern that you see over here is again not because of the roughness of the skin, means in addition to the roughness of the skin there are many organelles, many tissue constituents within the skin which is resulting into this speckle pattern. Okay. Okay, this is the speckle pattern that you see because of the interaction on the wall, because of the roughness of the wall. Then we talk about within the tissue as well. Okay, now what happens is that in real cases there are many tissue constituents, for example RBC, they are not constant, they are actually moving with a particular velocity. Okay, so after doing this after doing the autocorrelation, we can come up with a function known as speckle contrast. Okay, this is a parameter. Okay, that is defined as sigma s divided by average of I. This sigma s is standard deviation of intensity of speckle pattern and average of I is nothing but the mean intensity. So both of them you can actually calculate from that grainy image, and it actually will fluctuate. If you have something which is moving, then you actually it will fluctuate, and this speckle contrast will actually, so if you want to draw this speckle contrast as a function of delay, okay, you will see that it will actually die down after some time based on the velocity of your of tissue constituent. In this case it could be the RBC. Okay, so what it is it is seen is that the one which is dying very quickly is actually represent the velocity which is very fast. Okay, and the one which is dying very slowly, it correlates with the velocity of this tissue constituent which is moving slowly. Okay, so with this we can actually find some calibration, and we can actually find what is the, or we can correlate of what it could be the velocity of the flow of the RBC or any other tissue constituents. Okay. So that is the part that I wanted to cover in spatial coherence, the speckle contrast imaging. So this is specifically field of laser speckle contrast imaging, LSCI. We will discuss in more detail about this in a later session. I just wanted to introduce this as this is a part of the spatial coherence. So in this session, what did we learn? We talked about spatial coherence, which is started to differentiate what is temporal coherence and spatial coherence. It is more towards cross correlation, that is doing the correlation between the same wavefront as spatially shifted locations. Okay, so this is how you define it. Again, you normalize it. Okay, and then you one of the example, or that is way to measure the spatial coherence is Young's double slit experiment, where you compare the same wavefront at two different location. Okay, and then I tried to show you one of the example of the spatial coherence, that is the speckle contrast imaging. We started with the wall. Okay, it is having the roughness on the surface of the wall, because of which you actually see the speckle. And then you have the tissue, where below the skin of the surface there are many organelles, right. So these organelles can actually result into scattering of waves into different direction, which again leads to this speckle pattern, right. And then you have the RBC, which is kind of many tissue constituents. For example, RBC is also kind of moving. So you shine the light over here, but again you see different direction it is moving, and you get the same speckle pattern. Okay, but the difference of this speckle pattern is that this speckle pattern would be kind of vibrating. Okay, it would be something kind of bouncing up and down, right. So this intensity, it's the play of intensity that we can actually see the mean intensity as well as the mean standard deviation of this intensity. With that, you can actually say that how it is dying down. If you do the autocorrelation, how it is dying down quickly or it is slowly. Based upon that, we can actually comment, or we can actually correlate with the speed of the velocity of the RBC. Okay, so that's what we wanted to cover of the spatial coherence. So if you have any questions or doubt, you can please write to us and we will get back to you. Okay, thank you.